So in the last session, we talked about the properties of thermal radiation, where if I have a solid, liquid, or dense gas, that object will give off a smooth spectrum of light, will give off a range of different colors of light that depend on the temperature. The higher the temperature, the brighter that source was. So the higher the graph overall. And the higher the temperature, the more of that light was given off at shorter wavelengths, higher frequencies, higher photon energies. So the more the peak of this graph shifted to shorter wavelengths. What we want to do in this session is talk a little bit more specifically about this and how we mathematically describe this with two thermal radiation laws, the Stefan-Boltzmann law and Wien's law. And they're both going to still be talking about these general properties that we've been introducing. And when we talk about each of these, we want to be able to describe them in three different ways, both how these laws show up in practical examples, so in everyday examples, how do they show up on the graph? So how do they make this spectrum of light look different? And is there a way that we can quantify this with an equation? So let's talk about each of these properties. We've got the Stefan-Boltzmann law, which is basically the property that as temperature increases, the object gets brighter. So let me write that one down. So higher temp implies that object will be brighter. So more energy output per square meter. So more output, in this case, light output per square meter. And this also corresponds with that graph, that spectrum that we looked at was just getting taller. So the spectrum graph gets taller. Spectrum graph gets taller. And again, in the demo where I was showing the heating element of the toaster oven, we could see that as the temperature was increasing, it was getting just brighter overall. This is the Stefan-Boltzmann law. And then we also have Wien's law. In practical purposes, it's basically saying as the temperature increases, the average energies of the photons photons that are emitted also increases, or that wavelength of maximum emission gets shorter. So higher temp implies higher average photon energy. And in terms of the graph, that means the wavelength of maximum emission, where the graph reaches its highest point, that wavelength is going to go to shorter and shorter wavelengths. So for the graph, maybe the wavelength of peak output shifts to shorter wavelengths. Shifts to shorter wavelengths. We can get a little bit of a look at this from this graph. And again, we said at high temperatures, the graph is going to be very, very tall, and the peak of that graph is going to be at short wavelengths if we're at high temperatures. If we turn this down to lower temperatures, we see a couple of effects. First, the graph just gets smaller overall. It's not as bright as it was before. And this wavelength of peak emission, that's going to go, in this case, we have a lower temperature, so it's going to longer wavelengths. If we increase that temperature, that wavelength of peak emission shifts to the left. It goes to shorter and shorter wavelengths. So that changes the perceived color. Again, as an object's heating up, the first color that you see is this deep, deep red. Then it starts going to orange, to yellow. Eventually it's white hot. And then eventually it's so hot that it would actually look blue, because at these very, very high temperatures, it's giving off more blue light than any other part of the visible spectrum. It's also giving off a lot of ultraviolet light as well. So let's talk about how we're actually going to quantify this. So the Stefan-Boltzmann law is given by this equation. So let's talk about this in a bit of detail. We have this thing that we call the flux is equal to this weird little symbol, which is the Stefan-Boltzmann constant, times temperature in Kelvin to the power of 4. So let me write this out in a bit of detail. So flux equals this weird little symbol, which is just a number, times temperature to the power of 4. So we should label these. This is energy output, so light power output, per square meter. So basically saying every square meter of this object, how much light energy is it putting out every second? What is that power output? And this would be given in watts per square meter. If you think of watts, you might think of light bulbs. What is the power output of that light bulb? And in this case, we're saying how many watts per square meter. If I heat up this object, every square meter of this object is giving off this much energy. This weird symbol over here, this is the Stefan-Boltzmann constant. It's just a number. I'm going to list it out here, but we're really not going to have to use this one all that much. 5.67 times 10 to the negative 8. It's got these weird units of joules over seconds times meters squared times Kelvin to the 4th. It's got these weird units. And this is temperature in Kelvin. The basic idea here is that if the temperature increases, well, the flux is also going to increase. This light output per square meter is also going to increase. And since this is taking temperature to the power of 4, if I increase this even a relatively small amount, we get a huge increase in the overall brightness. So again, this Stefan-Boltzmann constant, it's talking about how hotter objects emit more photons at all wavelengths. So the higher the temperature, just the taller the graph, the more energy is being given out across all wavelengths. So what would this look like in a particular question? Well, the way that we're going to handle these Stefan-Boltzmann law questions is usually going to be in terms of a comparison style question, which we've looked at a couple of these examples for gravity. We're going to go over a couple of examples like this. So this one might ask something like, how many times more power per unit area does a 15,000 Kelvin star emit compared to a star whose surface temperature is only 3,000 Kelvin? So again, this how many times more power per unit area, that's talking about flux. So how is the flux changing with a high temperature star compared to a lower temperature star? So let's set this up and see how we would approach this question. We're being asked about power output per unit area, and that's flux. So we're going to be using this Stefan-Boltzmann law. So I'd recommend just write that down to begin with. Got that weird little symbol, times temperature to the power of 4. And we're comparing two cases. So remember, when we're doing these comparison style questions, we want our new case compared to some reference case. In this particular case, we're going to look at the flux of the high temperature star divided by the flux of the low temperature star, because we, again, want to know how many times more flux does one have than the other. So I'm going to write this as the flux from the hot star divided by the flux from the cold star. Looks like flux. Let me do flux from the cold star. If we can get this ratio, then we've got how many times more power output per square meter is the hot object going to have compared to the cold object. So let's just apply this equation in both cases. So we've got that weird constant, again, it's just a number, times temperature to the power of 4. And this is the temperature of the hotter object. In the denominator, well, we have the flux of the cold object. So that's that Stefan-Boltzmann constant times the temperature of the cold object, the power of 4. Now, that weird, when we're doing this kind of comparison, that weird Stefan-Boltzmann constant, well, what happens to it when we look at this fraction? Just cancels out. It's in the top of the fraction and the bottom of the fraction. So that term, we can just say those cancel out. We don't even need that weird number. But what do we do next? Well, we know the temperature of the hot object is 15,000 Kelvin. I'm going to drop the units for this. And we know the temperature of the cold object is 3,000 Kelvin. Now, at this point, there's a couple of methods that you could potentially use. This is a number. We could calculate what 15,000 to the power of 4 is, and then divide it by 3,000 to the power of 4. But when you take 15,000 to the power of 4, you're going to get a very, very large number that's very cumbersome to write out. It's easy to add or include too many or too few zeros. Maybe there's a better method. Well, if you remember your rules about how to use exponents, if I have 15,000 to the power of 4, and I'm dividing by 3,000 to the power of 4, these are both the same powers, then I can combine these together and just say 15,000 divided by 3,000, all of that to the power of 4. Again, thinking back to the exponent rules that you've probably talked about in some potentially long ago forgotten math class, if I have a fraction taken to some exponent, I can just look at the numerator to the power of 4 and the denominator to the power of 4. We're kind of doing the reverse for a reason that should be clear in just a minute. If we evaluate, like plug into your calculator, what is 15,000 divided by 3,000? Well, in that case, we just get 15,000 divided by 3,000 is 5. So I have 5 to the power of 4. And that's a lot easier to work with. If I do 5 to the power of 4, I get 625. 625. So in this particular case, we're saying the flux of the hot object, the power output per unit area, compared to the power output per unit area from the cold object, the hot object is outputting 625 times more energy per square meter than the cold object is. If you had different temperature objects, well, the setup for this would be exactly the same. You're just going to have a different temperature for your hot object and a different temperature for your cold object. So if I gave you different temperatures, like said, I don't know, the power output from a person, let's say the power output from a cold-blooded reptile or something, let's say that their body temperature is 290 Kelvin. So this is for a reptile. And for a person, it's around 310 Kelvin. If I wanted to know how much more thermal radiation am I giving off compared to a reptile, again, per square meter, I would be the hot object, the reptile would be the cold object. We change out our temperatures of the hot and cold objects and still get the same kind of method, the same kind of approach to this new question. And again, this is basically the primary way that we're actually going to be using this equation in this specific kind of comparison style question. Okay. So that's, again, the Stefan-Boltzmann law. We've got the higher the temperature, the brighter that object's going to be. If I look at the spectrum of light, the intensity versus wavelength, the taller that graph is going to be. And with this equation, if I increase the temperature, this flux, this power output per square meter, is going to increase dramatically as I increase the temperature. So that's our first thermal radiation law. What about this Stefan-Boltzmann law? In fact, I'm going to skip over that for just a second and look at Wien's law. So Wien's law is, again, essentially hotter objects emit more photons with higher average energies. And on these kinds of graphs, that means this wavelength of peak emission, as you increase the temperature, that wavelength of peak emission is going to go to shorter and shorter wavelengths. Remember, shorter wavelength light corresponds to a higher energy per photon. And specifically, the equation that describes this is the following. The wavelength of maximum emission times the temperature of the object always gives us this value, this 2.9 times 10 to the 6, and the units for this, we have to be careful, are nanometers times Kelvin. So let me be very clear about this. This is the wavelength of max emission. Wavelength of max emission. Specifically measured in nanometers. So this must be measured in nanometers. And just for reference, in the SI prefixes, nano means 1 billionth. So a nanometer is 1 billionth of a meter. There are a billion nanometers in 1 meter. So again, these wavelengths are going to be pretty short. This is the temperature in Kelvin. And again, that ensures that we get these same units at the end. So again, we've got this wavelength of maximum emission in nanometers. We've got the temperature in Kelvin, and this value over here is simply a constant. And the overall idea is this. If I take this equation and I increase the temperature, let's say I make this temperature larger. If this wavelength of max emission times the temperature must always equal a constant value, if I increase the temperature in order to keep both sides of this equation balanced, that wavelength of maximum emission must get smaller. Again, at higher temperatures, that wavelength of maximum emission is going to shift to shorter and shorter wavelengths. And this is Wien's law because this was developed by Wilhelm Wien. And he was the first person to actually calculate the temperature of the sun by looking at that spectrum of light, identifying what was that wavelength of peak emission, and identifying that the sun radiates most intensely at 500 nanometers. He was able to use this to figure out, oh, we can calculate the temperature of the sun from this. Let's actually give this a try. So the observations of the sun show the sun radiates most intensely at 500 nanometers. So that is the wavelength of maximum emission. So let's set this up. We've got lambda max times temperature is 2.9 times 10 to the 6. So that would be 2.9 million. So let me actually write that out as 2.9 million nanometers times Kelvin. We were just told that the wavelength of maximum emission occurs at 500 nanometers. And again, this must be in nanometers in order for this equation to work out. So 500 times the temperature is 2.9 million. And then, well, what would we have to do to both sides of that equation in order to solve for the temperature. We've got 500 times the temperature is 2.9 million. If I want to get temperature on its own, I have to divide both sides by 500. We divide both sides by 500. So the 500 cancels out on this side. And if we do 2.9 times 10 to the 6 divided by 500, I get 5,800 Kelvin. 5,800 Kelvin. Again, as long as I can identify what that wavelength of maximum emission is, if I know that wavelength of max emission in nanometers, I can plug that into this equation and calculate the temperature. Similarly, if I knew the temperature, I could work backwards and say, if I know the temperature in Kelvin, I can figure out what that wavelength of maximum emission would be. But most of the time when we're trying to look at the properties of stars, usually the easier thing to get is going to be that spectrum. We observe the star with a telescope, we break up that light, look at the spectrum, and identify where does that peak occur. And then with that information, we can determine what the temperature is. Just kind of going back to this discussion question, if the sun spectrum peaks at 500 nanometers, which is in the greenish part of the spectrum, why doesn't the sun's light appear to be green? Well, when we look at the actual spectrum of the sun's light, so this is approximately the spectrum of the sun. For this one, let me zoom in on this so you can see it a bit better. This top one is just a little bit higher temperature than the sun, but pretty similar. We notice that, yeah, its spectrum is peaking in the green part of the spectrum, but it's still giving off a lot of visible light across. It's giving off a lot of light across the entire visible spectrum. And when all of those colors mix together in our eyes, we perceive that to be white light. So it's an effect of the sun is giving off its light most strongly in the green part of the spectrum, but it is still giving off those other colors to a sufficient amount that when those colors all mix together in our eye, we perceive the sun's light to be white. Okay, so let's do one more example. This is the spectrum of a typical cool star. And again, it has lots of features that we're going to be talking about later on in the course, but we have some of the key features here where this spectrum, it starts low, swoops upwards, reaches a maximum, and eventually, if we continue this spectrum on, it would gradually slope down on the other side and go back to zero. But we can look at this and try to identify what is that point of peak emission. And if we know that wavelength of maximum emission, we can figure out what the temperature of this star is. So let's play around with this for a second. If we look at this graph, that spectrum follows approximately this shape. Again, there are these other little dips in the graph, some a little bit wider, some a little bit sharper, but we have some of those features included in this graph. We'll talk about what those features tell us about in future sessions. But if we look on this graph, that seems to be showing up, that peak seems to be showing up at around 720 angstroms. This particular graph is listing the wavelengths in units called angstroms. And just for reference, if you see one of these graphs in the future, 10 angstroms equals 1 nanometer. So if this is showing up at around 7,200 angstroms, if that peak of the graph is showing up around 7,200 angstroms, that's around 720 nanometers. So for this example, we have our wavelength of maximum emission is 720 nanometers. And, well, let's write out Wien's law. Wavelength of max emission times temperature is 2.9 million. The wavelength of max emission in nanometers is 720. And we're trying to find out what the temperature is. So in order to solve for temperature, what would we do next? Well, divide both sides by 720. And if we plug in those numbers, so 2.9 million divided by 720, when I ran through these numbers, I get a temperature of 4,028 Kelvin. This, of course, would be plus or minus a little bit, because did we find exactly the center of that highest point? Is it a little bit off? But we get approximately 4,000 Kelvin for this star. This is a little bit of a lower temperature star. If it were a higher temperature star, this graph would peak in a different part of the spectrum. It might peak somewhere over here instead, and we'd have a shorter wavelength of maximum emission, and that would correspond with a higher temperature. So that's Wien's law. If we can look at the spectrum of light from one of these stars, and we can identify what is the peak of the graph, at what wavelengths does this graph reach its highest point. If we can identify that wavelength of maximum emission, we can use Wien's law to actually calculate what the temperature of the star is. And again, these are just some of the properties of light that we're going to be using to extract information about the sources of these objects. In some of the next sessions, we'll talk about spectroscopy, Doppler shift, to figure out other properties of the stars by looking at the spectrum of light.